In this next section, we're going to focus on cardiac output as it relates to VO2 max. So this is the slide that we've seen several times. Before we get into exercise training, I just want to make note that exercise aerobic training also will affect things at rest, right? I've included our running man here. This running man will tell you that we're always dealing with aerobic training. If not, I'll specifically mention it. But again, this is what we've seen earlier in class. An untrained male, about 72 to 75 beats per minute is an average heart rate for male and female. Stroke volume, larger for male because of essentially body size. If you multiply them, at rest, cardiac output is about 5 liters per minute. Right? So one of the training adaptations that we'll see, though, is that although cardiac output does not change, right, we see a change in our heart rate and our stroke volume. Indeed, chronic exercise training decreases the resting heart rate of most individuals. Someone like Lance Armstrong, for example, has been known to have a resting heart rate of 32 beats per minute. However, in order to compensate then for the cardiac output, we have an increase in stroke volume. Actually, we can think about it the other way. As we're going to learn, stroke volume is going to become instrumental in changes in VO2 max. So ultimately what we see is an increase in stroke volume at rest. Therefore, we have a decrease in the number of beats that we need to push, right? So if we have more blood coming out in each beat, we don't have to beat as much. And it should be making sense to you now that the physiology behind our cardiac output is staying exactly the same, right? At rest, the metabolic demand is exactly the same no matter if you're trained or untrained. If you're sitting in a chair, that metabolic demand is no different. So if we then look at heart rate specifically, as we mentioned, heart rate at rest goes down. This is partially due to an increase in parasympathetic, which you'll remember is the negative effector, right? So at rest, heart rate goes down. If we look at its response to chronic training, I want to first start out with explaining what the graph looks like. So in all of our cube graphs that we saw yesterday in the previous module, what we talked about as instead of treadmill speed, we talked about this as percent of VO2 max, right? We made everything relative to working out as hard as you can and equated it to a walk or run, or a walk, a jog, or run, and an all-out maximal effort, right? For most of these responses to training, we're going to be dealing with, in general, the speed. So when we're talking about this, this is an absolute, a comparison of absolute intensities. Again, this has nothing to do with body weight as with VO2 max, but instead the relative is percent of VO2 max, whereas this is looking at who can run the fastest, the longest, right? So again, at an absolute intensity, our heart rate is less for each speed on the treadmill that we're running. So our post-training here is in purple. So as we increase speed, the heart rate is going to increase linearly, just like with our acute that we showed, a beautiful linear increase as expected. However, at each speed, it is lower. Right? I also want to add that we can say, here's our trained resting heart rate and our untrained heart rate. So again, as you can see, trained is going to adapt that. If we start talking about this as relative intensity, our response is actually not going to change, right? The reason that I want you to compare these is to, and my best way to make you think about them is saying at an absolute intensity that this person is actually working easier. It's easier for them to produce the metabolic supply and demand than it is for this person. So this, at this point here, this is at a higher percent of their VO2 max than this point is for this person, right? So on an absolute level, yes, they're exactly equal, but on a relative amount, this is relatively higher. So this person is closer to their VO2 max than this person is. If we make everything all relative, then our heart rate is going to be absolutely unchanged based on trained and untrained. So the other component of cardiac output is, of course, stroke volume. Stroke volume is greater at rest than it is at exercise, as we indicated in that very first table. Note that since Q is equal, that our stroke volume increases, heart rate decreases, just as we previously pointed out. Again, we're going to look at absolute training speed here. So as the treadmill speed increases, what does it look like for training? Heart rate was lower because it was easier, but we're meeting those metabolic demands by having a greater stroke volume. So at any given intensity or any given speed, we have a higher rate or a higher stroke volume. Not only that, but you'll see, as we talked about last week, the stroke volume usually plateaus. This is a little more real-world data, so it's not as pretty, but we would have a linear increase and then a plateau. So you'll see here that the linear increase exactly the same. However, the plateau occurs at a much higher speed. So hopefully you're already starting to get in your head this idea that that we're able to increase VO2 max because we have an increase in cardiac output, predominantly driven by this stroke volume. Right? As you can see, if we can keep that linear increase going, we can increase so many components in the cardiovascular system, deliver more blood per beat, and therefore have a higher VO2. If we look at it on a graph in that situation, right, for any given heart rate in an untrained individual compared to a trained individual, stroke volume is going to be higher in the trained individual. Right? So from this figure, we can look at each heart rate, the stroke volume is greater. So what we can then say is VO2 max increases, as far as cardiac output goes, is predominantly due to stroke volume. Heart rate doesn't play a big role. Our stroke volume is really driving improvements in VO2 max based on the cardiac output. So what we're going to do in the next lecture is we're going to focus on stroke volume itself.